So let's look now at this mathematical description of oscillation without damping. The situation we're considering is this: a mass bouncing backwards and forwards on a spring, and the size of the oscillation doesn't change, which means that the energy in the system is conserved. So we're not losing energy to the rest of the universe. That's what it means to have no damping. So to model the situation, we're going to need some equations. We're going to start with Hooke's law that says the force is negative k times x. So k is the spring constant, and the force is negative k times x, which says that when the mass is displaced in the positive direction, which is in this direction here, the force is pulling you back in the opposite direction. That's Hooke's law. The other law that we need is one of Newton's laws. That is that force is equal to mass times acceleration. I'm using some notation here that says the acceleration is x double dot, and what I mean by x double dot is the second time derivative of x, like this here. So hidden in these two equations, Hooke's law and Newton's law, is a differential equation of motion. We see this because these two forces must be equal, which means that negative k times x must be equal to mass times x double dot. If we just put these two things equal to each other, then we find that x double dot must be equal to negative k on m times x, and this is a differential equation of motion that we wish to solve. So here's our equation of motion. How do we solve it? Well, we're looking for something that oscillates. Let's take, for example, a cosine function. We could equally well choose a sine function. In fact, a cosine function and a sine function are only different by a phase, and there's an arbitrary phase phi in here, so it's kind of the same thing. But we're going to try this solution, x of t, and then see if we can find values of a, omega, and phi that allow us to fit this solution to the physical situation. So to see if this will work, let's first of all see if our trial solution can solve this differential equation of motion. So to do that, we need to know what x double dot is. So let's find that by first finding the first time derivative, which is negative omega a sine omega t. The cosine changes the sine. Then we take a second time derivative, the sine changes back to cos, and we get another factor of omega out the front. So this is now x double dot here, and we can substitute that into this side of the equation up here, and we can substitute x into this side of the equation here, and when we do that, we get this equation here. So now we have x double dot is equal to negative k on m times by x. And this is true provided omega squared is equal to k on m. This factor of a cos omega t plus phi is common on both sides, so all we require is that omega squared is equal to k on m. So if omega squared is equal to k on m, then we have a solution, which is that x of t is equal to a cos root k on m times t plus phi. And I've assumed here a positive frequency. We could take a negative frequency, but a positive frequency makes more sense, I think. Okay, so let's work our way through an example here. We'll start with a spring that has constant of 10 newtons per meter, mass of 2 kilograms. Initial velocity of the mass is negative 1 meter per second, so it's moving in the negative x direction. But its initial position is at positive 2 meters. And our job is to find the position x as a function of time. Now, we already know what this function looks like, it's just that we don't know the amplitude, the angular frequency, or the phase of this motion, but we know it takes this functional form here. So, we have to find omega, a, and phi. Let's start with omega because we already know the equation for omega. It's k divided by m. We know k and m, so very quickly calculate that omega is equal to root 5 seconds to minus 1, and we're assuming a positive omega in this case. Onwards to a and phi. How do we find these? Well, we use the initial conditions. So we write down equations like this and like this. This first equation here is for the position, so x at time equal to 0 is a cos omega t plus phi, and in a moment we'll set time here equal to 0. Our equation for velocity, x dot of 0, is given by this, so the omega at the front here comes from the derivative. and the sine comes from the derivative of the cos, and our initial velocity is -1. Now we set these times here equal to 0, so time here is 0, time here is 0, and this leaves us with a pair of equations, independent of time, for the two unknowns phi and a. Two equations, two unknowns. We can solve these. This is how we go about doing it. First of all, we square these two equations, allowing us to write an equation for the sum of a squared sine squared phi plus a squared cos squared phi. And using these two equations to get these two terms here, we find that the sum of these terms must equal to 4 from 2 squared and 1/5, and the fifth comes from this omega coming down underneath this 1. So we use sine squared plus cos squared is equal to 1, and then calculate that a squared must be equal to 21 divided by 5. Okay, so we know the amplitude of the motion. So what about phi? How do we find that? Well, we can take these two equations here and divide one by the other. We get sine phi divided by cos phi, we get a tan phi, like this here. And so doing this, we find that omega tan phi must be equal to 1/2, dividing these two equations by each other. Rearranging and using the value we know for omega, we find that phi must be equal to the inverse tan, arctan, of 1/2 root 5, or about 12.6 degrees. We have to also take care that we are in the right quadrant here. So we look carefully at these equations and we see that sine phi here must be positive and cos phi must be positive in order to have this being a +1 here and a +2 here. And so this angle here gives us the correct signs for sine phi and cos phi. So we're in the right quadrant because the inverse tan is not a unique function. It could be this plus or minus 180 degrees as well. But this is correct. So finally, we get this equation here for x of t. The amplitude is given by 21 divided by 5 square rooted. The angular frequency is root 5. And the phase is 0.22 radians, which is 12.6 degrees.